It's not a big deal. It's as if you have a function, you differentiate it and substitute at a point, or you differentiate it and stop. That's it. When you differentiate the function, you get a function, right? Another function. Okay? At any rate, what does this number represent, or what does this function represent? This is what is important to me. We discussed this a little bit last time. Let's discuss it again. You have a function, f, smooth function. Anybody doesn't know what do you mean by this, guys? Anybody doesn't know what do you mean by this symbol?
I don't.
C, A, B. Anybody remembers this? No? This is the space of continuous function. So when I'm saying f is in C, A, B, it means that f is a continuous function on the interval A, B. Simply, if I make this guy, so I'm saying that f is C1, differentiable function. So if I do this, it's twice differentiable. If I do this, it's infinitely differentiable, like sine and cosine. And this is the interval, the domain over which the function is defined. It can be anything. It can be an interval from A to B. It can be the sphere S2. It can be any M manifold, whatever. So this is any smooth function of the manifold. Why smooth? Because we are differentiating. We do nothing by differentiation. So we need to make sure that the derivative are defined. So we're working with a smooth function. So this v, little v, the tangent vector, takes a smooth function, differentiated, and gives you the real number after substituting at the point. This guy takes a smooth function, just differentiated, and gives you back another function. Well, what does this represent? You have a function defined on your world. Let's say this sphere is the Earth. Okay? This is the Earth. And your function is defined on the Earth, on the surface. What does it mean, a function defined on the surface? It means that give me any point, I'll give you a number, right? So let's say that this function represents the temperature over the surface, over the Earth. So maybe at the equator here, the temperature is hot. So along this line, the temperature is maybe 50 Celsius. Then it becomes a bit colder. Then it becomes maybe a bit colder. T is maybe 10. Then it becomes really cold there. Okay? It's a function. Give me any point on the sphere, I'll give you a number. This number just represents the temperature. Maybe I give you a number represent the humidity or whatever, any function. Pressure. Then I have this vector field. Maybe representing the wind direction. Okay? It's represented by a vector field. Why? Because this is the natural representation. The wind direction gives you a vector at each point. Right? This is actually the definition of a vector field. It gives you a vector at each point. So this is the wind direction, the wind velocity field. And if you throw a particle and let it flow with that wind, how much the temperature change of that particle? If it flows with that wind, it starts here maybe at 50 Celsius, and as long as it flows with the wind, the temperature changes, right? So the temperature of that particle changes as it flows with the wind. How much does it change? Is this guy. It's x applied to f. This is what? This is nabla f in your language without differential geometry. I don't need to know anything. This is your 200A, MAE, or the equivalent in civil engineering. The gradient of f dotted with a vector. This is what we call the directional derivative, right? Directional derivative of f along the vector x, which represents what? Represents how much f changes along x, right? Any question about that? And to compute it, it's easy computable, just differentiation. Okay? Any question, please? Any question? Okay. I think now you can appreciate why we had the example of the fruits and dates, because we're gonna keep writing this language over and over again. You need to understand it from the basics. Okay. Actually, this guy has a name in differential geometry, and this is the fifth word. It's called Lie derivative. So if we are given a vector x, this is a vector field. We want to build up language, right? It's like, I don't want every time to say x is a vector field on M. So I need to give it a symbol. The symbol will be gamma M, large gamma M. This is vector fields on M. The best thing in mathematics is that it gives you a language, but it's the worst thing at the same time, because now we have infinite words to learn. So now on, when I want to say this guy is a vector field, I'll say it belongs to gamma M. Okay, it's a vector field on M. What do you mean by a vector field on M? Well, it gives you a tangent vector at each point. Okay, so given some vector field and given function that is smooth function on M, we look at this guy. We define the Lie derivative of f along x. You can see from the description. This is what we're going to give it the symbol LXF, the Lie derivative of f along x. This is simply what we had from before, which is summation xj partial f partial little xj, which is in your own language is the gradient dotted with this guy. Okay? So this thing which we already know from before, the directional derivative of some function along a vector in differential geometry is called the Lie derivative. Yes, Mikhail?
The symbol that you're trying to explain with vector fields on M, this symbol, what is it? It's an L, a C, or?
It's gamma. Gamma. See, I'm defining a symbol and I'm even sloppy defining it. Any question about the Lie derivative? It's the same thing as the direction derivative. Yes?
Could you please explain once more what do you mean by this belongs to a vector fields on M?
No, it's like I'm saying, you know what do we mean by vector field? Well, okay, the collection of all vector fields on M, we give it the same. We give it a name. We denote it by gamma M. So now on, when I'm trying to say, let X be a vector field on M, I'll simply shorthand it as X belongs to gamma M. It's exactly the same like here. What's C infinity M? Is the set of all functions smooth acting on M. So when I'm trying to say, let F be a smooth function on M, I just do like this. It's the same here. It's a language, okay, more than anything else. Okay, so this is the Lie derivative. Any question about the Lie derivative and what does it mean? Do you have anything about how to compute it or what does it mean? The Lie derivative. Any question? I mean, we just introduced the Lie derivative now, so it has nothing to do from before. If you have a question, it's perfectly legitimate. Please don't feel shy. And you can see the things are becoming more and more mathy, as I promised in the first lecture.
What exactly is the difference between vector view and Lie derivative?
Say it again, please.
What are the differences? Why are they using different words?
For what? Different words for what?
So one is called vector view, one is called Lie derivative.
No, they are not the same thing. The vector field is here. The Lie derivative is not the vector field. The Lie derivative it's called the Lie derivative of some function along the vector field. The Lie derivative is not the same as the vector field. The Lie derivative is the same as the directional derivative of f along the vector field. The vector field is a vector. Okay? The Lie derivative, what does the Lie derivative give you? It gives you how much this function changes along this guy. Okay? The result of the Lie derivative, Lxf, which is this guy or that guy, the result is a function. Right? If you evaluate this function at a point, it gives you how much this function changes along the vector field at that point. If you evaluate it at another point, it gives you how much this function changes along that vector at another point. Okay? So for example, here is, say, at the equator, T is 50 Celsius, okay? And I have a vector field that is, when it comes to the equator, it gives you direction eastward. Okay? How much the temperature changes along that vector? 0. So the Lie derivative of that function, the temperature function, along that vector will be 0. Okay? Any question about the meaning of the Lie derivative or how to compute it? Okay, I'll move next. What the hell this has to do with